Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, let's get started. All right, so just before we begin, just a reminder of a couple of things that have sort of come up in email, and just in case you haven't been here at the start and the other couple of days. So just a reminder that from this afternoon I'm going to be out of town for a couple of days. So if you need to ask me a question, you can still email me. I'm going to be stuck in meetings pretty much all day tomorrow and Friday. So I might not be able to answer your email immediately, but I will get to it as soon as I'm able. So that's going to be the easiest way to contact me, just by email. And I'll be in Perth, so I'm 2 hours behind, okay? So factor that in. Second thing is, again, just a reminder about the assignment in case you missed what we talked about the other day. So just from questions I've been getting in email, the singers data is in the class data, okay? So if you go into R and you can't find it, you load the class data and you will be able to find it. In general, if you load the class data, pretty much any question that begins with where is the ... the stuff we do in this course, it's in the class data if it's not in base R, okay? So load the class data and your answer is right there. And then the second thing, again, there's been some questions around the format of the assignment. Let me just repeat very quickly what I said before. So 4 pages, okay? That's 4 sides of a page. So could be 2 physical pieces of paper, could be both sides, or 4 one-sided pieces of paper. Yes, it's a hard limit, okay? So 1 line over, I just stop reading. And again, this is not me being arbitrarily mean. It's just that, you know, if you're going to have a rule, it's got to be the same for everyone, because if I say, oh, it's okay if you go 2 lines over, then it's got to be okay for everyone to go 2 lines over. Then it becomes 3 lines, and then I've got 100-page assignments to deal with. That ain't happening, right? So, and look, the truth is, if you can fit it in 4 pages and 2 lines, you can fit it in 4 pages, right? There's an art to writing things shorter. Learn it. Again, lots of questions around choices of graphs. Again, the answer is you make the choice, okay? There's no point asking me, should I put this graph in? The answer is always going to be, if you want to, okay? And that does not betray any sense of whether to do so is right or wrong or good or bad, but it's your choice, okay? And so, I mean, I just can't make those choices for you. And I'll tell you, there's 2 reasons why, right? One is that sort of silly reason that, well, it's your assignment and I'm marking it and all that, you know, stuff. We get that. But the other reason that it's your choice is that people can make different choices and both do a good job if the writing that's around those choices supports those choices well, okay? So you might decide, you know, I'm going to put histograms in or whatever. And you might use those histograms to make an argument that tells me what's going on with this data, okay? And someone else might decide, oh, I'm going to put QQ plots in. Now, my best advice is pretty simple. If you put something in, use it, okay? If you put histograms in and then as a picture and then you don't talk about them, guess what? You shouldn't put them in, okay? So try and think of this thing not as, you know, what graphs, pardon me, what graphs are going to please the person reading it. Think of it as what graphs best support the arguments that I'm going to make, and also try to remember that the graphs don't exist in isolation, right? They're supported by and they support the arguments that you make, the writing that you do, okay? And the whole thing has got to hang together, right? Let me tell you a story. One year, somebody handed in 4 pages with no writing, just 4 pages of graphics, okay? Now, I might have agreed that these were good graphics to describe this data, but that person still got 2 out of 10, right? Because what am I looking at here, okay? I'm like the person who went into the cave and saw the pictures and it's like, okay, yeah, I don't get it, right? So it's got to hang together. And that's why there's no sort of one answer as to, you know, should I put this in or should I put that in, okay? And the graph has, the data has secrets that graphs will reveal. And some of them are really obvious and some of them are really not obvious, but if you look hard you'll see them. And you know, how far you go along that journey is part of the game. And so I just encourage you to play. So yeah. So again, I really don't mind if you email me these questions, but you just be prepared for the fact that the answer is going to be pretty much the same every time, which is it's your choice if you want to, yada, 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 okay? Because I don't have better answers than that for you, unfortunately. And you don't really want me to have better answers because really I know that for some people, and this is just psychology at work, for some people asking me the question is a comfort thing, right? I'll feel better if you give me a particular answer. Okay, life lesson number 7. Feeling better, don't make life better. Okay, it just doesn't. Okay, I'm old enough to actually know something true about life. Good things last 3 seconds, bad things last 3 weeks. Okay, so when something good happens to you, you're all happy. It takes about 3 seconds for that to wear off, right? You get over that real quick. When something bad happens in your life, 3 weeks later you're still like, ooh, right? So I know emailing me and asking me questions you know I can't answer might make you feel better. I don't mind you doing it, but believe me, it's not going to help you. You'll feel better for 3 seconds. Yeah. Anyway, all right. Back to the rats. So we've been working hard trying to understand these rats, and you know we've got this graph here, and we've talked a lot now about what is the curve that everybody wants to put through this graph. Okay. And yesterday we talked a lot about the non-parametric approach. So kernel smoothing and low S smoothing. So let me just remind you again what those things do. Each of them works on the same basic idea. They basically take the data and they divide it up, if you like, into little slices, right? And they sort of say, okay, in each slice, I think the data is not doing anything very exciting. So I'm just going to fit something really simple to that slice, okay? And then I'm just going to slide that slice across and join the dots as I go. That's essentially what both methods are doing. And K-Smooth takes one approach and it says, I'm going to use little slices and I'm just going to fit a very simple model, a flat thing inside each slice. It's a flat thing. It's not too simple because there's that kernel which produces some sort of averaging. What it's averaging is the Y values. Okay, so again, I just want to point out the difference between this and what we did in one dimension with histograms and densities. With histograms and densities, same idea, but what goes on inside each little window or kernel is not the average of the Ys, because there are no Ys, it's essentially a weighted count or a weighted proportion of data that's in the slice. Okay? Now we've got Ys, so what we do with the kernel is we do essentially a weighted averaging of the Ys. Low S does something more complicated, it fits a little polynomial, but, you know, potato, potato, right? It's essentially doing something really simple in a little slice. The other thing that low S does different is that it lets the slices get bigger or smaller depending on how spread out the data is in the horizontal direction. So, you know, down here where there's lots of data crammed in small spaces, the windows are kind of small, the kernel has a very small window width. But when you get over here, where the data's kind of spreading out in the X direction, the windows get bigger. And this is designed to let the line be as smooth as possible, all right? And, you know, we drew the line yesterday. I'll draw them again here now. So lines, K-smooth, we'll do both of them, K-smooth, X and Y. Where are we going to go? Kernel equals n for normal. Okay, and we'll have, I think we settled on a bandwidth of 10 yesterday. So band equals 10 will do it. LTY equals 1. Colour equals, I don't know, purple. Okay, that was the normal one. Looks more magenta to me, but I don't know. And here's the low S one, and we talked about this yesterday. Remember, low S uses this option of F equals to determine how big the windows are. So you go low S, X and Y, none of this kernel junk, this disappears. Again, we're going to have a solid line, but we're going to make it, what goes well with purple? Green, thank you. Whatever, right? It's a lime green. Yeah, that looks like the Canberra Raiders, sort of. Yeah. Okay. We see that they're different, and we talked about why they're different. And again, it really relates to both the window width being a different kind of concept between the two methods, and then so what happens is this one here can't really respond as quickly to the way the curve changes, right? It's got a fixed window width. This one does a bit better. So if you were going to choose one of these to always use, I mean, low S is pretty much an unbeatable choice, right? So in real life, whenever I want to do some scatterplot smoothing, I just always use low S, okay? No matter what. I never use the kernel smoothing method. But historically, it sat before low S, and it was a precursor to that development. So we talk about each of them. Now, non-parametric methods have great strength in that when the data moves, they move, and so they're very responsive to what the data does, okay? But they're really bad at one thing, and that one thing turns out to be pretty important. And that one thing is prediction, right? Because you've got the curve here, and it's fine where you've got data, but as soon as you run out of data, I mean, and even right at the edge, right after you run out, you don't get the line, and you don't know where it goes. I mean, you can guess, but that's just a guess. So you're not going to be able to predict based on this curve. You can interpolate within the scale of data that you have, but extrapolation is difficult. So that's problem number one. The other barrier to prediction is there's no formula, right? These things don't have simple formulas. So even if I want you to interpolate and I say, well, look, tell me what the value of Y is, what's the hormone level when X is 9, I mean, you can't just plug 9 into an equation and tell me the answer. You've actually got to do it more or less graphically, you know, here's 9, pop up here, pop across here, okay, it's about there, wherever that is, right? Maybe 8, I don't know, okay? And that's not very satisfying for people. People don't like that. People like precision. They like it too much, truth be told, but they do like it. So these are not compact descriptions of data. They don't lend themselves well to prediction. You don't get a formula. All three of these things make people deeply uncomfortable. They are, at the moment, purely descriptive, right? And that's about it. Parametric models, on the other hand, don't suffer from any of these defects. They have defects of their own, okay? The first defect is we don't know what parametric model fits this shape, right? And when we first breached the topic, we got at least 3 different answers, right? Parabolic, quadratic, exponential, all of which can be fit to this data. Nothing prevents you fitting those models to the data, okay? And each of them would look sort of like this data looks because each of them have that shape, right? They start flat and then they start to curve upwards. But they have different sort of signatures, right? Quadratics curve up at a particular rate, exponentials curve up faster typically, and so on. So when you don't know what shape this is, you're in a world of pain when it comes to fitting a parametric model. You just kind of got to hope that you're close. So that's a difficulty with parametric models. On the other hand, they lend themselves very, very well to telling me what Y is when I tell you what X is, because there's a formula and nothing prevents you predicting off the edge of the data. So provided you don't go nuts and try and predict hormone level when blood loss is 70-12, I was going to say, that's a silly number, 87, which is way, way off the end of that data, right? As long as you sort of stick to numbers that are just a little bit north of 25, you're probably okay with your predictions, okay? Whereas with the low-S, you don't have luck at all. So if we're going to pursue parametric models, and that's where we're headed next, you really need to find a way to make this look unequivocally like a shape we all recognise, okay? Now, we can cut to the chase, plot x and y and log y, and I showed you this yesterday. Did you lose something? I bet you left your thumb drive behind.
No, it's the cover for it. Is it all right if you just keep going?
Oh, yeah, well, you can look for it. It's all good. There's nothing worse than losing the cover of your thumb drive, because then you've got an uncovered thumb.
No, please just go ahead. I'm happy to just...
No, that's all right. All good. Okay, so this is the shape we end up with. It's lost, probably forever.
It's my pointer.
Oh, no.
You haven't seen it, have you?
I have not seen a pointer. No, I use this.
You can reach further.
Yes, I can.
You see, technology making people equal.
You can go even higher. Good luck.
Okay, thanks.
All right, so here's our shape. Okay, so what shape's this? Straight line, right? Looks like a straight line. That's all cool. But let's do what we did for the other data before, right? We used our fingers. Let's use our fingers, right? No harm doing that, because straight line looks okay, right? So we can all do a straight line with our fingers. But really, remember I encouraged you to do is to use two fingers, okay? And sort of see something interesting here. It looks okay, but it's sort of fat down this end, skinny in the middle, and it sort of starts to get fat down the other end as well. So this might not be homoscedastic. It might be a little bit non-homoscedastic, okay? Now, here's something weird, right? We're going to pretend it is homoscedastic, that is constant variance. So in other words, I'm going to pretend, because it's going to be convenient to do so, that as you move your fingers from left to right, they go up in a straight line and they stay the same distance apart. And the reason I'm going to do that is because I want to fit a model, and I want that model to be reasonably simple. And I can't think of even a halfway simple model that does sort of narrowing and then re-widening. And that's nasty, right? So we're going to pretend that this is homoscedastic. Now, this raises a really important point, right? Because you can look at that and I can look at that, and we can both agree, I think, that your fingers shouldn't stay the same distance apart, right? What do your eyes tell you? And yet I'm telling you I'm going to fit this other model. Well, welcome to the world where models are wrong, okay? And guess what? It's the world you've been living in all along, because models are always wrong. And there's a very famous saying about this, attributable to a statistician named George Box. And he said, all models are wrong, but some models are useful. And that's kind of where we're at, okay? That's kind of where we're at. By the way, you guys would have heard of machine learning, right? It's a big deal these days. And what machine learning is trying to do is to build, essentially, very complex black box models, okay? So in other words, they're not like regression lines where I can tell you an equation and you've got a hand calculator and you're good to go. You can tell me what's going on. These are models where I build the model and then I just tell you I've got a model and you can ask me what y is when x is whatever, but I can't tell you anything more than that. It's a black box. Inside is dark. Okay? These models tend to fit the data you have really, really well. Okay? In fact, one of the criticisms of machine learning models is they tend to overfit to the data that you have. So they try to mimic features of the data by adding parameters to the model. So you get very big models, very chatty or greedy models. And they're wrong too, because what tends to happen is even though they fit really well to the data you have, as soon as you go out and you get new data, they start to fail. Okay? So probably some of the best examples of this, there's a really famous example which relates to flu trends. So every year they try to predict when the flu's going to come and how bad it's going to be, and they use this information to get you to go out and have a vaccination, or at least to make sure that vulnerable people are vaccinated. So it's pretty important. And ever since anyone can remember, the predictions on the flu model, on the flu incidence, was done by the Centers for Disease Control in Atlanta, Georgia. And they base their model on medicine and on statistics, and it's basically an epidemiological model. It's a model of how disease progresses through a population, okay? And historically, they've got it pretty much right, okay? Not exactly right, because every year's different, and you might already know this, every year the flu changes. It's a real bugger, right? You get vaccinated one year and you think you're good to go, but you're vaccinating against last year's flu and it's changed, right? So you might still get it, etc., etc. So they do their best using the best available epidemiology. Okay, about 10 years ago, Google decided, I'm going to see if I can predict, when the flu, I anthropomorphise Google, I'm saying them as a person. They decided, the company, to look at searches for flu symptoms. And they tried to look at how searches for flu symptoms were surging at particular times of the year, and they were able, in the first year they did this, to accurately predict when the flu surge would begin and how intense it would be. And they actually beat the CDC's estimates. They did really well. And they were very happy with this, let me tell you. They came out and they said, you know what? Who needs the CDC? We got this, right? We can just use search. And, this isn't just going to work for flus. This is going to work for a lot of stuff, right? Because what people search for is going to be on, it's going to be what's on their mind, and that's going to predict what's actually happening in the world. And people got really excited, and people actually started to say, machine learning is going to be everything. It's going to answer every question we ever had, because look at what Google did with the flu. 2 years from then, they tried it again, and their model got it really, really wrong. You can look it up. You can see stories on the net about it, about how the Google flu trends just failed a couple of years on. And the reason is that they were confusing, again, so epidemiology is based on causal models, right? Google's fantasy was that correlation and causation were actually the same. Because yes, it is true that searches for flu go up when the flu starts to hit. But that's correlation, that's not causation, right? And so, you might say, well, why did the thing fail? Because you might think there's a causal model in there somewhere, right? People hear about the flu, start to search, people start to feel sick, they start to search. Well, it turns out people heard about this thing, so they started to search. And so it fed back on itself. And so it gave elevated estimates of incidents when there weren't incidents occurring. Correlation, causation, different. So black box models, they look very alluring and very promising. They tend to have heaps of parameters. They tend to use all of these parameters to estimate really fine features of the data. And this gives people a false confidence that these models are somehow correct, right? And this is fed into by this weird notion that machines know better than we do. They don't yet. And we ought to be happy about that, because when they do, we're in a lot of trouble. Now, why am I talking about this? I'm talking about this because we're going to fit a simple model. And here's the truth. Simple models drive decision-making much more effectively, typically, than complex models. And this is despite the fact that people think complex models are better. And this gets to this thing we talked about before. People want the wrong thing. Everybody wants more information. The problem is, more information overwhelms your ability to cope, to understand, right? Almost all of your understanding is built on simple analogues for complex things, okay? And you deal with complexity through experience by building little add-ons to your model. We talked about this right on day one when I talked about the picture of the smiley face, and I said, what's that? And everyone says it's a face because it's got the key features of a face, but it doesn't have a nose, and it doesn't have ears, and it doesn't have eyebrows. And we build all that stuff in later, okay? And those adjustments to the model help us update our world, okay? So it's perfectly okay to go for simple models, and when you can have a simple model that works okay, you should treasure that and not seek to overly complicate it just for the sake of it. Okay? So, we're going to fit a simple model, this straight line model. So let's fit a straight line to it. It's really easy to fit a straight line to data in R. You just go AB line, because it's only got two parameters, A and B. AB line, LM, log Y, tilde, X, okay? Dollars coefficients, or coef will do. Okay, there's the line. Now, when you look at it, it looks okay. It seems to track the data pretty faithfully. Goes through the middle of the data all right. Because R has gone ahead and fit the model, I can tell you what the coefficients are. They are these. Intercept is 0.432, slope is 0.138. That means that the log of y, and put a hash in front of this so that R doesn't try to calculate stuff, log of y is equal to 0.432 plus 0.138 times x. So that's the model that we've gone ahead and fit. Now, remember, we live in a world where you guys are in a class of statistics, so you've done some maths, so you're not scared of log functions, right? But for 90% of humanity, logs are where snakes live. That's it. And so you don't want to give your model out as a log. And the other thing is, if someone says to you, what's y when x is 8 or whatever, what you don't want to be saying to them is, well, log y is that, because that's expecting them to do a calculation they ain't going to do. Okay? So when you express your answers back in your assignments and all that stuff, I want you to back out any transformations you use, because it's disrespectful to walk up to somebody and speak a language they don't understand. Okay? I realise that just describes every lecture you've ever been to, but that's life, right? So we're going to back that out. So that means y is equal to e to the, not next, exp, e to the 0.432 times, plus 0.138 times x. And then you can use the rule of exponents to expand through that. And you should write it out. You should try to write it out as a times x to the b, right? That's the way you should end up writing it. Now, I should point out one thing here, which statisticians tend to worry about. When we write down linear models, what we typically write is response equals a plus b times explanatory variable. Oh, typing's gone to hell today. Plus error. Okay. That's how we normally write out a statistical model. We normally have additive errors. When you fit the model, the error disappears because your error is always estimated to be 0, even though in every instance that it occurs it's not, but your estimate is that it's 0. So when you write that out, the error part disappears. And then when you back transform, there's no problem. But do think about what happens to the errors when your response is on the log scale. So we'll come back and think about that later. But I just want to plant that seed just for the minute, okay? So we'll come back to that. So that's the model that we've ended up fitting. Now, it's not the entire model that we've ended up fitting. We've done one other thing. If I look more carefully at this model, LM log y tilde x, I can get more detail about that model in R by going summary of that model fit. Copy, paste, here we go. Copy, paste, there we go. Okay, so you get a bit more information than you probably wanted. But see, there are your coefficients, okay? Where are we? Over here. There are your coefficients here, so 0.432, 0.138. Each of them has standard errors, okay? So we get an idea of how variable our estimates are, okay? Now, the next two numbers in the little table you get here, t-values, this is what you get if you take the estimate and divide it by the standard error. And it's the answer to the question, how many standard errors is my estimate away from 0? Okay? Now, in the case of one of these two numbers, that's a sensible question to ask. Because if this number here, 0.138, is a lot of standard errors away from 0, then it means that your line isn't flat. Because 0 slope means flat line. Okay? And if your line is flat, then there's no regression and there's no relationship, or at least no linear relationship between x and, in this case, log y. Okay? So the t-statistic here of 16 tells you that you're a long way from having a flat line relationship. Okay? Now, the t-statistic for the intercept is 4.8. That tells you that your intercept estimate is 4.8 standard deviations away from 0. Who cares? Who said it was going to be 0 anyway, right? So this one here doesn't make a whole lot of sense because it's testing against something that isn't a reference point that we care about. So you're only ever really going to look at this one, okay? Unless you had a suspicion that the intercept was 0, but why would you suspect that? All right. Then the other thing I'm going to point out is, where is it? Oh, it's here somewhere. Here. Residual standard error, 0.6166. That's your estimate of S, or sigma, right? Your error variance, your error standard deviation, I should say, 0.6166. Okay? So a standard linear regression model produces 3 estimates: an intercept, a slope, that tells you where the line goes, and then that third one, 0.6166, basically tells you how wide that river is that you cast out with your 2 fingers. Okay? And it's a single number because we're indulging in the fantasy that your fingers stay the same distance apart as you go across. Okay? So that's what that number is. And all the rest is the usual nonsense that you get from F-tests and so on. I will draw your attention to one more thing, R squared. R squared's 0.76. In a simple linear model, R squared is the proportion of variation explained by the model. So a linear model explains 76% of the variation in this data. Okay? So we look at that and we think, that looks pretty good. I'm pretty happy with that straight line. If someone says to me, what's y when x is 8? It's dead easy. All I've got to do is I've got to go e to the, 0.432 plus 0.138 times 8. And that's the value that y should be. It should be around 4. Okay? It should be around 4. Let's see if that's reasonable. Let's go back and plot x and y. When x was 8, about here, up and across. Yeah, close enough. Okay? Close enough. So it does okay. So that's my linear model. All right. Now, we got lucky. Boy, did we get lucky, right? Because I showed you x versus y, and then some sort of miracle occurred where I kind of knew that log would work, so then I showed you x versus log y, and everyone went, oh, it's straight. I don't have to think anymore, right? But that was, how did I know? How did I know this, right? I mean, let me tell you, I'm no expert on rats. I have no idea why a logarithmic relationship or an exponential relationship should work here, okay? So I just lucked out. And you know what? Most of the time as a statistician, you don't know the underlying physiology or medicine or physics or whatever it is you need to know to work out what functional relationship will work, right? And I remember you said quadratic, right, when we first looked at this. So what we could do is we could look at y versus x squared, say, and see if that's kind of linear. Because if that's kind of linear, then maybe we're good to go with the quadratic, right? So instead of plotting x versus log y, if I wanted to do that quadratic thing, I might plot x versus square root of y. So let's see what happens. So there's x versus y. So have a look at that. Now I'm going to plot x versus square root of y. And again, this comes from the idea that I just don't really know what's going to straighten this thing up. Okay? I lucked out. So this is a plot of x versus square root of y. What do you reckon? It looks straight. Who thinks it looks straight? Okay. It's interesting. Who thinks it's not quite straight? Some people voted twice. Good one. Okay. I agree. It's not quite straight. I mean, it's close. It's closer, right? The other one was sort of zzz and then straight up. This one is kind of and then just a little bend and then slowly up. But it's not straight. It's not quite straight. And you kind of know it couldn't be, right? Because if log y straightened it, how could square root y? Because square root's not quite as strong as log. Okay? So your eyes defeated your brain there. That's cool. Most of us, that happens for almost all of us most of the time, believe it or not. So square root did sort of half the job, but not quite, and log does it a bit better. Okay? So this is better than we were originally, but it's still not perfect. Still a little bit of a curve. By the way, if you want to see the curve, probably the easiest way to do it is to try actually put the line on and you can just see what happens. So AB line, ln square root of y till the x dollars cof, and you'll see it. Actually doesn't look too bad. Doesn't look too bad. I think there's just a hint. How do you know it's still curving? I'll tell you. Down here, most of the points are below. Up there, most of the points are above. That's the sign that it's starting to move up faster than you're happy with. The other thing that you'll notice by putting this line in is that the spread doesn't behave itself quite as well. It's still skinny down one end and it's just starting to pull apart at the top end. Okay, but it's a close call. It's a close call. By the way, here's the thing. You could fit x to log y, or you could fit x to square root y, and both are okay models, right? I think the log model is slightly better. I think it fits to the data slightly better, but it's a close call, right? And so you've got two competing models that are going to give you different answers, but they're both okay. And so there's where you start to have to make finer judgments around which one works better than the other, okay? And these are tough judgments to make typically. Okay, let's talk a little bit about how you choose transformations, because that's a tough one. And it's a tough one because there are infinitely many transformations that you could choose, all right? So we're going to introduce this idea of what's called power transformations, and we're going to really try to use those because they're quite compact mathematically, okay? And you can actually make some sense of how the powers bend the line, okay? So we're thinking here of transformations like, so we're going to call these power transformations. So they are x to the power a and y to the power b. Those are the sorts of things we're thinking about, okay? So typical transformations are, if you let a be bigger than 1, you get cubes, squares, right? X to the 1 is just do nothing. Then if you pass below 1, you get fractional transformations. So x to the power half is a square root. X to the power 1/3 is a cube root. Okay? Log sits below all of the fractional powers. It kind of sits at the 0th power for an odd reason, because you can think of it as an integral of a power of x, right? And so these different powers have different strengths, okay? So power 1 is do nothing. If you move away from 1 to 2 to 3 to 4, they bend the line more and more. Think about how x squared compares to x cubed. X cubed rockets up a lot faster than x squared. So that's the line bending, okay? And as you go down from 1 to a half to a third, you'll bend in the other direction with increasing power, okay? So what we have in mind here is trying to take an existing shape and bend it into a straight line by using these power transformations. Now, there are 4 pretty simple shapes we can think about. Okay, so I'm going to draw them up here. So there's this shape. Okay, there's this shape. Then there's this shape. and then there's this shape. These are kind of the four shapes that you might get in a simple scatter plot that has an increasing or decreasing relationship. By the way, if your function is wiggly, you're probably out of luck in getting a simple transformation to fix that, okay? Now, you guys remember high school maths, right? What does this look like? Y equals what? X squared. Okay, could be x cubed. It's x to the something where a is bigger than 1, okay? So it's a polynomial, it's rising faster than the straight line, so you're looking at this, okay? Okay, so that was an easy one. Everyone knows that one. What about this one? What does this look like? What's a function that looks like that? Who remembers? So square root of x looks like that. Cube root of x. Log x looks a bit like that. Okay, so these are the kinds of functions that have that shape. Okay? You remember this from school, right? What's this one look like? Thank you. Well done. 1 over x squared, or x to the minus 1, x to the minus 2, and so on. Okay? So, what's the common feature in these three so far? They all look like y equals x to some power. If the power is bigger than 1, it curves that way. If the power is less than 1 but bigger than 0, it curves that way. If you breach 0 and go to the negatives, it goes this way. What's this look like? Yeah, maybe. To me, it looks like, what if I did this? It's starting to look like a circle, right? What's the equation for a circle? Who remembers that? X squared plus y squared equals c squared? Something like that. So, what's the point of telling you all this, okay? The point of telling you all this is that power transformations basically give you the building blocks for pretty much any simple shape that's curved. As long as it's monotonic, that is, it only goes in one direction, you can capture any of these kinds of shapes with simple power transformations, okay? So, if you see something that's curving upwards, like this, you can try this, okay? By the way, in the land of mathematics where there's no errors, I don't have to write it as y equals x squared. I could write that as square root of y equals x just as easily. And this is one we looked at before, right? Because we tried x versus square root of y. And so you can see you can do it either way. Okay, so depending on the shape that you've got, you're going to try these different kinds of transformations. Okay? Now, data has errors. Okay? So, the question of which you transform, let's talk about this one over here. The question of which you transform, x or y, depends on what the errors do. Okay? Because the errors will either be constant on the original scale, or you'll have heteroscedasticity on the original scale. Okay? So what I'm going to do now is I'm going to draw you two more pictures of this one here. Oh, someone's put a thumbtack. Oh, I better not just throw it and probably end up puncturing something. Okay. So let's rub all this out. You know, when I started teaching, it was a long time ago, this was all done using chalk. And here's a quaint idea. People used to write stuff down. Now I see people take photos of the board. Isn't the world great, the way it's changing? Okay, so here's my shape, okay? So, by the way, if you're wondering why am I doing this on the whiteboard, it's so I can use different colours. I get to indulge my artistic side. So, let's imagine, and if you're listening at home, read the notes. It's all in there, okay? If your data did that, if your data has a sort of a constant spread around the curved line, then you're homoscedastic here, but after you transform you won't be, okay? Now let's think this through. If I transform x, what's going to happen to that spread? Not a lot, because the spread is vertical, okay? Spread's a vertical thing. We worry about the spread vertically. So y is the vertical ordinate variable, that's the word I was looking for. Y is the vertical variable, x is the horizontal variable. If I just spread this out, the vertical stuff's not going to change much at all, okay? So if your data looks okay with constant spread, to begin with, when you transform it, you'd better not mess with y, you'd better mess with x. So for this one, I would take y and I'd leave it alone, and I'd take x and I'd move it to x squared, and I'd plot y versus x squared, and I'd see what I get. Okay? Yeah?
Aren't we basing these models that y is the response period and we need to only transform x?
No, you can do whatever you want. So, y is the response variable. If you transform it, then yes, when you communicate your answers, you'd better back transform those. So you're still talking about the response. But in terms of the modelling itself, x and y can take on whatever form is most convenient to fit the model. Yeah. Okay. So, now, half of you guys are sitting over this side. So let's go over here. Okay. There's my shape again. This time, what colour was it? Green. Oh, I'm already out. Damn. Okay. This is more like the data we had. This is more like the data we had, right? So the data curves up, but it gets more spread out as it goes, okay? So what do I do here? Well, if I transform x, all that's going to do is stretch that out, but it's still going to look like a trumpet, right? Skinny at one end, big at the other, okay? What if I transform y? What happens to small numbers when you square root them? They stay small. What happens to big numbers when you square root them? They get small, right? Think about it. Square root of 1 is? Here's a tip. Answer the easy questions. Because when the hard ones come, you can say, I already answered a question. Okay? So, square root of a small number, you get a small number. Square root of 1 is 1. Square root of 2 is 1.4, which is about 2, and so on. Okay? What's the square root of 100? 10. That's a lot smaller than 100, right? What's the square root of a million? I'm asking you the easy ones. It's 1,000. It's a lot smaller than a million. So if I square root this, not much is going to happen here, down the low end, but up here, where it's spread out, these are going to come closer together. So when I square root it, it's going to basically leave these the same, compress those. Okay? So it's going to take that flare out, and it's going to control the flare at the upper end and leave it more or less alone at the lower end. It's going to leave the spread where you want it. So, we now have a set of ideas around how you can transform data to achieve both straightening the scatter plot and getting the spread characteristics right. Okay? So the golden rule is this, and we'll show you some examples next week. The golden rule is, look at the shape you've got. Try and match it up with one of the functions that we've talked about here, these simple power functions. Okay? Then, ask yourself, was the spread okay at the start or not? If it was okay at the start, transform x. If it wasn't okay at the start, transform y. Okay? So that's the baseline rule that we're going to use. Now, until you see that in action with real data, it's all theory. Okay? But you have to wait until next Monday, unless you want to play with R yourself, which I can't stop you doing. So, over to you. See you next week. Hey.